Okay, so I think we can start. So in the last lecture, we started talking about unsupervised learning. And in unsupervised learning, we talked about GPLVM, we talked about probabilistic PCA, we talked about factor analysis, and we talked about dual PCA, right? And that was the end of our discussion on Gaussian process. And starting today, we will be continuing on unsupervised learning, but we will be going into more advanced unsupervised learning algorithms. To be more specific, we will be going into generative modeling algorithms. And the idea is to try and cover two generative modeling algorithms, which are kind of the most popular ones. One is the normalizing flow or invertible neural network that we will talk about today. And then we will also talk about diffusion, which is perhaps the state of the art today, which we will also be talking about. So that is the plan for the remaining of the course. I remind you that whatever we are going to discuss today and today onwards is not in the syllabus for the major. So it's not included in the syllabus for the major, but I believe these questions are perhaps there in homework 4. So you should check. I think it is there. Practical, it is not there. Practical has also been uploaded today, by the way, the last practical. But homework, I believe these questions, there will be questions on normalizing flow at least. Okay, so that is the idea. Now there is one problem here, by the way, as we start or try to discuss normalizing flow. As I said, that these are all based on neural networks, and we have not discussed neural networks in this course. So the idea is that I will be talking about normalizing flow because this is a kind of a concept that does not really need neural network to discuss. So we'll be talking about it without explicitly talking about neural network. I will give you a brief overview of neural network in the practical on Wednesday. And so the idea is that, and that will not be recorded again, the Wednesday one. And the idea is that this normalizing flow you can use with any model, but generally it is used with neural network. So you will see that the concept we will talk about is basically on a function. So that function can be a neural network or that function can be anything else. Okay. So we will be talking about that. Okay. So with that, let us start. So can you remind me what is the objective in generative modeling that we discussed last time? What is the objective of generative modeling? So in generative modeling, what are we trying to do? What are we trying to do in generative modeling? We want to generate new samples, and which we can only do if we at least learn the distribution implicitly. Explicitly is fantastic, but that might not be possible. So mostly implicitly. So that is correct, but how do we do that? And this concept was common for, let's say, factor analysis also we were doing this. GPLVM also we were doing this. What were we doing there? Latent variable z, and we are trying to map from a latent variable z, or which is low dimensional potentially and easy to sample from, like Gaussian, and we are trying to learn the mapping from that latent variable or the hidden variable z to the output x, and we want to learn the mapping so that the mapping is from Gaussian, let's say, z to x, which is the unknown distribution. And if we can learn that mapping, then life is easier, because now I will generate new samples for z, map it, pass, and I will get new samples of x. So without explicitly learning the distribution, we are able to generate samples, right? So in generative modeling, we attempt to learn the mapping M that maps from Z to X. Okay. So in generative modeling, we try to learn this mapping M, which is a kind of a function that will map from Z to X, right? That is the idea. And the key takeaway or the key things to note here is that Z is from some known distribution, known and easy to sample, not just known distribution, right? The first key takeaway is that Z is from some known distribution, and when I say known, I mean known and easy to sample, right? Okay. So basically known distribution from which we can sample. Okay. That is one aspect. The other aspect is that we will potentially want Z to be low dimensional. Okay. So we will potentially want Z to be, Z belongs to our, I don't know, D, where D is potentially, and I am using the term potential because it may not always be possible to do that, potentially low dimensional. Okay. We will want to do that. Why? The reason is that if Z is low dimensional, X will potentially be high dimensional. So whatever we are mapping, that will be having less number of parameters. Okay. So that is the idea. But this low again has a threshold. You cannot expect Z to be one dimensional. That might not have enough information, enough feature. So what is the dimension of Z often becomes a hyperparameter. So to give you some example, Z can potentially be 100 dimensional, whereas X can be, let's say, having thousands of pixels. Okay. So even 100 is much lower when it is 100 cross 100 or 1000 cross 1000 pixel. So in that sense, it is even then it is low dimensional. But 100 is not low dimension. So when I say low dimensional, it means relative to the dimension of X. So that is to be understood when I say low dimensional. Okay. So this is the idea, right? And this is the idea we have discussed last time. This is nothing new. So now, if we take a step back, okay, this is all fine. We have done this last time. We have done this using probabilistic PCA. We have done this using factor analysis. All of those we are doing this thing only, right? But let us take a step back and try to think what exactly are we trying to do here. What exactly are we trying to do? If you think about it, what we are trying to do is we are trying to transform the distribution of Z to distribution of X. If you think about it and take a bird's eye kind of or vision, then you will realize that all of this thing is fine, but these are only medium or way for us to achieve transformation of distribution. Because at the end of the day, I want to transform from distribution of Z to distribution of X. Right? That's what we are trying to do. So if you think carefully, all of this thing we have discussed last time, but at the core, our idea is to transform Z into X, to transform the PDF of Z into PDF of X. That is our goal. And if you can do that, you can sample from the obtained PDF of X, and that will be your new samples, right? So if you think carefully, fundamentally, fundamentally we want to learn transformation of distribution. Okay. Fundamentally, we want to learn transformation of distribution, right? So to do that, let us assign some distribution. So let us assume that Z is from FZ Z. So Z, the sample is coming from some PDF of Z. Okay, this is the PDF notation, and this is one of the what are the examples of this? Can you give me some examples? What distribution FZ might be? Gaussian. Anything else? Uniform. So some known distribution, right? It can be Gaussian, it can be uniform. Mostly it is Gaussian, but sometimes it is taken to be uniform. Okay. Then we have X, which is coming from X fxx. What is this distribution? Unknown. So this is an intractable distribution. You do not know this distribution. You only have data from this distribution, but this distribution is not known to you. Okay, so this is unknown distribution. Right? Now, is this enough for transformation of distribution, or do you need any? So what we want to do is we want to transform or learn the transformation between fzz and fxx. So fundamentally, we want to express fxx in terms of fzz. Correct? That's what we want to do. Now, to do that, what do we need? We also need one more thing, which is how x and z are related, the samples. So let's, and our generative model, exactly that is what we were doing. We are learning m z to x, so that m should be there. So we also assume that x, this is a small x by the way, and this is small z. So x, which is a potential sample, is equal to g theta z. Okay. So let us relate it with what we have done in the last lecture. Last lecture we did factor analysis, right? Or probabilistic PCA. So can you tell me what was the form of g theta in probabilistic PCA? Can you remind me? In probabilistic PCA, what was the form of g theta? What was the form? W times z plus epsilon. Right? X was equal to Wz plus epsilon, where epsilon was from a Gaussian with 0 mean and sigma square I variance. In factor analysis, it was equal to Wz plus epsilon, but epsilon this time was from 0 with and 0 mean and psi as covariance, and psi was a diagonal matrix, but each diagonal can be different. Right? So that same thing, if I generalize, I can write in this form. What is theta here? Parameters. What was theta in probabilistic PCA? Weights. Right? What were the parameters in factor analysis? Weights. Right? So you can relate it with what we have done last time. All I am doing is I am generalizing it in terms of a function parameterized by theta. Now this function, once I parameterize in this manner, this can be anything. This function can be a neural network. It will be a neural network in this case, but it can also be a Gaussian process. It can be some polynomial chaos expansion. It can be any function, radial basis function, any functional, any machine learning model, supervised machine learning model you can think of. It can be any of support vector machine. Okay, it can be any of those. Okay. So clear what is this g theta? So now, given this, and I know we did it long back, but can you remind me how fzz is related to fxx. Can you remind me the transformation of distribution formula? Let's say only for univariate case. Multivariate we'll do later. We'll do now only, but just the univariate case. Can you remind me? What is the relation between fxx and fzz? How were they related? Yeah. And what was the formula? You are correct. That the area should be constant. That's what we did. And how did we found it out? Correct. And then you take dx or dz to the other side, you will get it, right? So we have done it exactly correct. What we did was, if you remember, transformation of distribution. We have done it earlier, and I told you that we will need it towards the end of the course. So now we are there, because we did it, I know, lecture 2 or 3 maybe. So f x x dx is equal to f z z dz. So this is from where you find it out. So you will take dx to the other side. So what will you get? So which implies f x x is equal to f z z dz dx dx, right? This is for the univariate case. What will be the formula for multivariate case? We have done that also. There is just one change. What? Del z by del x. And what will happen to the absolute determinant, right? So for multivariate case, so n variate PDFs, the formula remains the same actually. Z determinant del z del x. Okay, clear? Any questions? If not, let us try to relate it with where we started, right? We started with this thing, generative modeling, which is a continuation of last lecture, and we want to generate samples of x. Okay, and we assume that you can generate low dimensional z from some known distribution, transform it with some function, which is g theta in this case, and that will give you samples of x. So the idea is that can we learn this whole, do this whole business? Because to do this, we will need to find out theta. Theta are the parameters which is unknown. So theta is to be found out, right? And we know that essentially this is what we are trying to do. At the end of the day, this is what we are trying to do. So the question is that, can we use this concept to find out theta? And when you use this concept to find out theta, that is known as the normalizing flow. Okay? So the question is, can equation 1 be used to find theta? Okay. So now you tell me, if I want to use equation 1 to find out theta, somewhere in equation 1 theta should be present, correct? Equation 1 should be function of theta. So how is equation 1 related to theta? I don't see any theta here. So where is theta in equation 1? Del z by del x. Why is that a function of theta? Z and x are related by theta, but that is x is equal to g theta z. From there, can you find out this del z by del x, or do you want something else? It has to be invertible. So what you will need is z is equal to z theta inverse of x. Only if you know that invertible form, then you can take a derivative of that, and that will give you this Jacobian term. Correct? So the first thing we need is that our g theta should be invertible. Correct? The first thing we need is our g theta to be invertible. That's why invertible neural network, or that invertible name comes into picture. I'm not going into neural network. I'm explaining it without neural network as such. I'm just explaining it in terms of some function. Okay? But that function has to be invertible. Okay? So we'll come to that, and that theta has to be invertible, but still, how will you find out theta? How will you find out theta? Because to start with, theta is unknown, right? And if theta is unknown and you give some arbitrary theta, will this fxx be fxx? For any theta fx, this will not give you fxx. Fxx is a true distribution, right? So this will not give you fxx. So what will it give you? So let us change it. So what will happen is, you want fxx, and that you can potentially get if you learn theta exactly, which possibly you will not be able to do. This will be equal to q theta x. What is q theta x? What notation you use for q? Some approximate distribution, right? This is approximate because theta is not yet trained. And even if you train, you will get q theta x only in an approximate sense matching with fxx. Correct? And why? What is theta? Theta are the, what are theta? Same theta parameter. This is coming into picture because there is del z sitting there, del z del x, that will be function of theta. So that's why the theta is coming outside. So just to summarize, what we are doing is as follow. We want to learn the mapping from z to x. So we assume it to be some function parameterized by theta. If the parameter theta are exactly known, then we can exactly find out fxx. But the parameter theta is to begin with is unknown. So with the unknown theta, we can get an unknown distribution parameterized by theta. That distribution we are denoting as q theta. And the objective is that we will try to tune theta so that it matches what? Fxx. So then what is your loss function? KL divergence between the two. So you have data for x, and you will want your data generated from your model g of theta to match those x. So you will want KL divergence between q theta x and fxx to be as minimum as possible, right? So with that background, the answer is yes. By formulating a loss function L of theta is equal to KL divergence between, now KL divergence is not symmetric. So which one should I take? Forward or inverse? I can take either actually, but generally in this case forward helps. Okay, and I'm going to ask this question, why forward helps or how forward helps. So think about it as I write down the expression. Between, I said forward, so fxx and q theta x, right? This is equal to what? The expression for KL divergence? Integration fxx log of fxx by q theta x dx. Right? Clear? Any question? Now, the next line I will write, but before that, okay, let me write it down, the next line, and then I will ask you the question that I promised with respect to fx log of fxx by q theta x. Right? So now, can you tell me how forward helps, or what are we going to, how are you going to compute this expectation? How are we going to compute this expectation, or why did I choose the forward and not the inverse? Okay, so how? QS fx will ignore, that I understand, but still there is fx is there in the expectation, and fx is unknown, so fx is intractable. So then how does it help? The whole problem is not the numerator of log. The problem is the fx outside, right? That was always the problem, and that problem still is there because it's expectation with respect to that. Correct? So why this form, and how does it help? To start with, what will you have? In generative modeling, to start with, what will be available to you? Samples of x. So we can use those samples to approximate this expectation, because I will have n samples of x drawn from or available to me from fxx. Fxx is unknown, but I have n samples from there. I'll use the Monte Carlo approximation and approximate this expectation with those samples that are available to us to begin with. The whole idea of generative modeling is what? You have n samples. From there, can you now start generating new samples? So those n samples we can use to express this in a summation form. So this is then approximately equal to 1 by n summation log fx xi q theta xi summation over I. And I am assuming I have n data points. Now, as correctly pointed out, the numerator is useless, right? So this is equal to minus 1 by n summation over I log of q theta xi. So if I remove the negative sign, I can work with just maximizing this. So I now have a loss function which is in terms of q theta, which is equation 1, and I can maximize that or minimize that with a negative sign to find out theta. Correct? Is this clear, what we have done? Any questions? So let us call it equation 2. Okay? Clear what we have done? We have written the expectation by using the training samples that are available to us, and those training samples are not changing, so my expectation remains the same, whereas theta was changing. So if I have reversed it, for every time the expectation would have been with respect to a different q theta, because theta changes to q changes during training, I'm saying. Okay? So theta can be computed by minimizing equation 2 or maximizing log of sorry, summation is there. So let me by maximizing summation over I log of q theta xi 1 by n, right? We can either minimize equation 2 or maximize the negative of that. That's what I have written, correct? And by doing that, I can find out the theta in theory. But this will only be possible if I can evaluate q theta to start with, right? So, however, to evaluate q theta, there are the following conditions are to be met. Conditions are to be met. And you will tell me the conditions. So, let me go back. Here is the expression of q theta. So, what are the conditions that are to be met to evaluate this equation 1? Repeat. Invertible is 1. So, g theta should be invertible. So, x is equal to g theta of z should be invertible. Anything else? Anything else? Determinant is not only non-zero, it has to be non-zero, and along with that the determinant you should be able to evaluate quickly, because every time you have to evaluate it while training. So, you should be able to not only should be able to evaluate the determinant, but you should be able to do it extremely fast. Otherwise, your training will take forever. So, the Jacobian should be non-zero, determinant of the Jacobian actually, the determinant of the Jacobian should be non-zero, and we should be able to evaluate it fast, to evaluate it quickly, right? So, these are the two conditions. So, let us go one by one. So, first thing is g theta should be invertible, right? So, the question is, what do you think, is any g invertible? So, the first condition is g theta should be invertible, right? So, my question is simple, what is your opinion on this statement? Or rather, no matter what the form of g theta is, do you think it is always invertible? And when I say invertible, I mean 1 to 1. I mean, right? So, if you give one z, you should get one x. If you give that x, you should get that z back. So, is it always invertible? No, right? And we know that even a square term is not in 1 to 1, it will give plus minus value. If x square is equal to 4, x is equal to plus minus 2. So, even in that case, it is not 1 to 1 invertible in the 1 to 1 sense. So, forget about a nonlinear function being invertible, right? So, definitely nonlinear functions are not invertible, linear functions are, right? Y is equal to ax plus b, you can always find out x in terms of y minus b by a, right? But nonlinear functions are in general not invertible, right? Any arbitrary function may not be invertible, and that is the challenge, okay? This is challenging as any arbitrary function may not be invertible. Okay. And why are you talking about invertible or arbitrary function? Because you will ultimately that there will be some neural network coming into picture. A neural network gives you arbitrarily nonlinear functions. So a neural network definitely is not invertible. I mean, you cannot guarantee a neural network to be invertible. Similarly, computing the determinant of the Jacobian, again, that might be tricky, right? So that's why this is coming into picture. So this is not straightforward. And because g theta being invertible is a necessary condition that is to be ensured, but this is non-trivial. And that's where come the design aspect, that how to design g theta that is so that it becomes invertible. Okay. So the question is, can we design g theta that is expressive and invertible? Why am I including the term expressive? Because yes, you can design a linear g theta that will always be invertible, but that might not be necessarily expressive enough. Because even a linear regression model you cannot use here with higher order basis function, because higher order basis means nonlinear in Z and then it's not invertible. And with linear basis, that not at all expressive. Correct? So, can we design g theta that is expressive and invertible? So, let us start and take a scenario and let us see how we can proceed with designing g theta. Okay? And in the process we will be talking about the determinant part also. But maybe in the design process we address the determinant part as well, because that is another important aspect, right? Okay. So let us start with the simplest case, and the simplest case in this case is not 1D but 2D. So the simplest case is a 2D grid. So let us take a 2D grid. And what we do is, when I am talking about transformation, right? So you can think of it as creating a grid and transforming the grid. You can think of it like that. So let us create a grid so that we can track how the grid might transform. So let's say I divide the y-axis into 3 and x-axis also. Okay. So this is my initial grid that I am generating. Okay. And I will give this axis a name. Let's call it x. Let's call it y. Okay. What I will want is that I will want to pass this x and y grid points through a function, vector evaluate function, and that should give me x dash and y dash. And I will want that this function that I am passing it through should be invertible. So if I give x dash and y dash, I should be able to reconstruct x and y. So that means this function should be, I should be able to go from x and y to x dash and y dash, and from x dash and y dash to x and y. Okay. So I will not draw it, but I will just write the axis. So I want to find out, or rather, maybe let me call it x1 and x2. I prefer that. So I should be able to go from x1 dash. Okay. Clear what we are trying to do? So let us see. So suppose we decide that my x1 dash I am not going to touch. This is invertible. This is identity met. So obviously same. This I can do. And x2 is what I am going to deform. and deform not in just any manner is equal to x2 plus m of x1. Okay. So now this is my forward pass. I will call it my forward pass because I am going from x1 and x2 to x1 dash and x2 dash. What have I done here? I have designed it very clever in a very clever manner because I know x1 is equal to x1 dash. So I can if I know x1 dash, I can always reverse it. And what will be the backward pass? Can you tell me? From here, just tell me the back. In backward pass, I want to write x1 and x2 in terms of x1 dash and x2 dash. So what is the backward pass? Start with x1. What is x1 equal to? x1 dash. And remember, when I'm saying backward pass, I'm not talking about gradient or something, just backward mapping. What is x2 equal to? x2 dash minus m of x1 dash. This is my backward pass. Right? So this mapping is invertible. I'm not saying it is the best mapping in the world, but this is at least invertible. Correct? So now, how will the plot look like? First of all, x1 dash will not change because x1 dash is equal to x1. So that means the vertical lines will remain as it is. How many were there? 3. And what is about the horizontal line? The horizontal line can change, but it will change as a function of x1, right? So that means even if you change x2 location, the line will not change with x2, it will only change with x1 because m of x1 is there, right? So if I take a x2, maybe this will look something like this. So this will become parallel actually. Okay, this is parallel. I mean, I might not have drawn parallel, but they are supposed to be parallel because the line is changing with x1. For a given x2, it will not in that sense, right? Clear? Now this you might argue, and you should argue, that this is not expressive enough. I'm not changing in one direction, right? But no one is telling you that you will only do this transformation once. So next time you do the transformation, what will you do? You will fix x2 and change x1. So next time, what will it look like? So next time, let me write it here. So, okay, wait, let me give myself space where I want to draw. So next, what I will do is I will find out x1 double prime and x2 double prime. Okay. So now tell me, what will x2 double prime look like? x2 double prime will be equal to x2 prime. So this time I am fixing x2. And x1 double prime will be equal to x1 prime plus m of, and this can be m1 and m2. This need not be same again. I mean, I am writing m, but it may be m1 and m2. Maybe I should write m1 and m2. m1, m2 of x2. Right? So if I now use this, what will it look like? Again, this is again invertible, by the way. Okay. So given x2 prime and x1 prime, I can always go back to x1 and x2. I just have to go back 2 times. So what will this look like? So now this will remain as it is. And this can now change, x2 can now change with x1. X1 now can change with x2. So maybe this will look, I don't know. And by doing this multiple times, you can understand you will get a very complex kind of representation, right? So it's not like you are going to do this one time, you are going to do this multiple times. Okay? Any doubt till now? If there is no doubt, I am going to now introduce one terminology, and I am also going to justify the name, and then I'll come back and talk about limitation and modify it. Okay? So first let us start with terminology. What is this called? I said normalizing flow. Why is it called normalizing flow? What is the justification of the name? So you can think of it like this. You are kind of flowing like a water from Z to X and X to Z. So you are getting transformed from Z to X or X to Z like a flow. Now it is not a continuous flow. I mean, it will be neural network. Each layer is like a stop. So it is flowing through the nodes and the functions that you are going from Z to X and X to Z. That's why the name flow comes from. Why normalizing? Normalizing because Z is generally taken to be normal distribution. So any X you give me, I am normalizing it to be a normal Gaussian distribution. So a flow that normalizes X to Z. That's why the name normalizing flow. Normalizing because it normalizes X to give you Z, which is Gaussian distributed. And flow because it is flowing through the network nodes and all those things. And it is flowing, it is evident because you see one forward pass is not enough. You have to do it multiple times, I said, right? So that's the flow. So from the top left diagram to the top right, that's one flow. From top right to middle right, that is the second flow, and you will have multiple of those. So that's why the name. Clear? Second thing, forward pass. So this has a name. This is known as coupling layer. This is known as coupling layer. Why coupling and why layer? It is known as coupling because it is coupling x1 and x2. So there are two variables that is coupling, one as a function of other. So they are getting coupled. That's why coupling. Layer because in neural network you will have multiple of this. So one is one layer. Okay. So that's why layer. Coupling because it is coupling x1 and x2. Layer because you will not have one of these transformations, you will have multiple of this. So each one is a layer. Clear? Any question? So now, let me ask you one question. Do you think this mapping that we have written is expressive enough? Because I told you that we want a mapping that is expressive enough and invertible. This is definitely invertible. But is it expressive enough? Or do you think it's not? And why? Obviously, why is the more important question? I can always, because you can understand that by doing this multiple times, you can get very complex shapes. So that might give you the impression it is expressive enough. But actually it is not. Because if you look at the determinant of the Jacobian, what is the determinant? What is the Jacobian of the first one? It will be a 2 cross 2 matrix. So what will it look like? The first one will be 1. The last one will be 1. And then it will be a lower triangular matrix. So the determinant will be equal to 1. And I will show you that. And what does determinant of Jacobian denotes? Change in volume, ratio, or in this case change in area. So what does it mean if it is 1? That the area is not changing. So each square can deform in a very complex shape, but the area will remain the same. That means it's not expressive enough. It should have changed its area also. If it is not changing the area, that means it's not expressive enough in that sense, right? And you will want a transformation that allows you to change area of the small squares, right? So the coupling layer is volume preserving. Okay, what does it mean? It means that del x dash by del x, if you find it out, that determinant of that. So determinant of, you will get what? Del x1 dash by del x1, del x1 dash del x2, del x2 dash del x1, del x2 dash del x2. And I hope you have done this, the fact that Jacobian, the determinant of Jacobian is equal to area or volume in your linear algebra, or at least in solid mechanics. I think this is common thing, right? This is what you will get. Now what is this equal to? This is equal to determinant of 1. x1 is not a function of x2, so x1 dash is not a function of x2, so that will be 0. This one I am not writing because this is 0, and this will be 1, or rather, so which is equal to 1, right? What will be this equal to? This is x2 dash x1. x2 dash x1 will be m1 dash, something like that, but that is, you may or may not write it. Okay, clear? So this shows that it is volume preserving, so that, or area preserving in this case. So that means each of the square, they will deform in a very complex shape, but the area remains constant, and we don't want it. So how do you change it? So to address this, this affine coupling layer was introduced. Layer was introduced. Okay. Affine coupling layer was introduced. And affine coupling layer, how does it look? x1 dash is equal to x1, remain as it is. Okay. Coming to x2 dash, x2 dash is equal to, previously, let me write what it was previously. It was x2 plus t of x1. What I have done is that I have made m into t now. Okay. What do you think t is denoting here? Translation. Okay, because when I say it is area preserving, that means these things are getting translated, but they are not getting scaled. And that's why the area is not changing. The scale is 1, right? So it's not changing. So that means I will introduce scale also. And how do you introduce scale? By multiplying something with x2. Correct? But the problem is that you don't want it to be 0. Right? So we will write it in this form. So therefore exponential of s of x1 multiplied by x2 plus t of x1. So this is done to ensure that that never goes to 0. Okay. So this is my affine coupling layer. This is called affine because this is the affine transformation that you find in Gaussian distribution. Affine coupling layer. Okay, and this is the forward pass obviously. What will be the backward pass look like? Simple. x1 is equal to x1 dash, x2 is equal to x2 dash minus p of x1 dash multiplied by exponential of minus s x1 dash, or divided, but it's exponential of minus s of x1 dash. Okay, clear? Now s here is known as the scale factor or scaling. S corresponds to scaling, t corresponds to translation. Who will give you this Tx1 and S of x2, S of x1? How will you know that? Those are the things that will be modeled as a neural network or generally neural network. So this T of x1 and S of x1, this becomes your trainable parameter. So the theta that I was talking about earlier will now be sitting inside those. T of x1 will be semicolon theta, S of x1 will be semicolon theta. So it will become T of theta x1 and S of theta x2. Okay. So T of x1 translation S of x1 scaling, and both are modeled using neural network in general. By the way, I will give you a recap of neural network on Wednesday, as I said earlier, because I am talking about invertible neural network without talking about neural network, but I am mostly talking about function. That's why. I mean, it need not be neural network. It can be any function. T of x1 and S of x1 can be any function and it will still be invertible. Okay, neural network, because neural network is very expressive and all those things are there, right? Clear? Right? Now, what is the determinant? Or the Jacobian, let's say, del of x this, del of x, if I have to find out, what will it look like? First term will still be 1, right? x1 is equal to x1 dash, so that remains 1. Second term will still be 0. Third term I still don't care about. Fourth term is the important one. What is the fourth term? X2 dash x2. That will give you exponential of S of x1. Exponential of S of x1. So now the determinant is non-zero, more than 1, assuming this is positive, but it's not 1. Okay. I mean, obviously this will always be positive, sorry, not assuming, exponential is there, but yeah. So now it's not volume preserving. The volume can now change, the area can now change because the determinant is now greater than 1. It can also be 1 for some value of S or some specific S, but it can be greater than 1 also. So that is more generic. Okay. One more thing. This I was doing for 2D, right? In general, x1 and x2 need not be scalars, because I was doing for 2D means x1 was a scalar, x2 was a scalar, but x1 and x2 individually can be a vector. That's also possible, and this thing still works. So this still holds, I mean almost holds, if x1 is d1 dimensional and x2 is d2 dimensional. Okay. How will it look like now? In that case, your x1 will be x1 dash, x1 dash will be x1, that will not change. It is x2 that will change. So x2 dash will be equal to exponential of S of x1 and then Hadamard product. What is Hadamard product? Element wise multiplication. Okay. So which means the dimension has to match. Yes. Okay. Element wise multiplication with x2, I guess, plus t of x1. Okay. And this exponential, it is kind of obvious, but it's also element wise. I mean, we will find out this S of x1, each element of that element wise we will make it exponential, and then element wise we will multiply with x2. So this whole business is element wise. Okay. So exponential is like, yeah, some nonlinear operator, nonlinear activation applied element wise. This is point wise or element wise. I think element wise sounds better. Element wise product. Okay. Clear? Any doubt? For this case, what will be the Jacobian like? For this case, the vector case, the generic case, del x dash by del x. How will it look like? Identity matrix. So it will become block matrix. So one identity matrix of dimension d1 cross d1. So right. So this is a block matrix. The second one will be zero matrix, null matrix, d2 cross d2. Bottom left, I don't care. I will not write it. It will be some complex matrix, but that will not matter. Bottom right. This is interesting. What will be the bottom right be? It is element wise, right? So exponential will sit in the diagonal. Others will be 0 because it is element wise. Okay. So it will be in the diagonal, you will get exponential of s that will sit. Others will be 0. Okay. So this will be exponential of s1 x, and that's a diagonal kind of matrix. And the dimension will be d2 cross d2. Okay. So d1 cross d1, d1 cross d2, and in that manner you will get. Okay. Clear? And so your determinant will be equal to, what will be the determinant equal to? So, correct, which is trivial to calculate. That was, so our second objective or second compulsion or need is satisfied. So determinant is can be trivially computed. So this transformation provides us or addresses that issue as well, right? Which means determinant of del x will be equal to product over exponential s1 x j product over j, something like that. Okay. Clear? So that means that we now have a transformation that can be used for vector space also, and the determinant is still can be trivially computed. That is what it means. Which means with this transformation we can actually build a model that can be trained based on equation 2 that we discussed earlier, which is this one, right? Clear? Any doubt? So then the question is that how do we actually use it? Because in reality we will not have x1, x2. In reality we will have one vector of x of dimension, some dimension, that even we might have one matrix, not vector. Today we will only talk about vector, next lecture we will talk about matrix. But let's say we will have one vector, okay? A time series, kind of, multiple time series as I have, right? So I will not have this x1 and x2. So how do we use it in practice? So the discussion till now is based on x1 and x2, right? But in reality, we will not have x1 and x2, we will only have x. x1 will be our first data point, but not dimension, right? So, in reality or in practice, we will have data is equal to xi. This is what we will have. Okay, and our x I belongs to, I don't know, something like this. Correct? This is what we will have. So, in that case, how will you use this concept that we have discussed today? How will you use this concept that we have discussed today? So, how to use the affine transformation? Any idea? How do you use it? That is the splitting you are saying, not sampling, splitting. That is one idea. That is actually the first idea. So, the idea A is splitting. What you will do is that each of the sample you will split into D1 and D2, such that D1 plus D2 is equal to D. And that you will do randomly for each layer. Because if you keep it fixed, then some portion you will never learn. So that means all the portions should ultimately be undergoing some transformation. So that split should change. So that's why it's random. You are right. So splitting means you have this one. Let's say a vector of this with these elements. So from here you will create two vectors. Okay, and this might go here, this here, this here, this here. So randomly we will do that. And in each affine coupling layer you will do it randomly. So it will not be same. So that each portion of that data undergoes some transformation. Clear? This is one way. There is another way where you don't have to do this random business with the splitting part, and that is based on random linear projection. Random linear projection. Here what you do is you have x. So from x you find out x tilde. By multiplying it with it, how do you do a linear projection? You multiply with a matrix. So by multiplying with a matrix S. Okay. And then, so this is a random projection matrix. Okay. And then you will find out x1 and x2 by splitting x tilde. And this splitting can be deterministic. Why? Because randomness is there in S. Okay. Give me some good choice of S that you think can be a good choice of S based on the requirement that are there. What are the requirements? It should be invertible, which anyways it will be, and the determinant should be easily computed. Now in this case, because you are multiplying with S, the determinant should involve determinant of S also, right? So that means S should be something where the determinant is preferably known already. So do you know of any projection matrix where the determinant of S is known or trivial to compute? What is the determinant of a rotation tensor? In solid mechanics you have done 1, right? Sine and cos and all those things comes. So a good choice of S is it can be a rotation matrix or tensor. I mean, we'll call it matrix here. but in mechanics sense, it is tensor. Okay. A good choice of S is rotation matrix. But again, you should remember S is supposed to be random, which means that for each layer you should select different S. Don't keep on selecting the same S, then it will be problematic. So switch the rows and all those things you can do, but be it random in each affine coupling layer. Okay. So the remaining portion I will let it, it is not complete yet. We have not even talked about any network or anything. We have just talked about the foundation. And this foundation we talked about because you don't need neural network to talk about this foundation. So we'll come to neural network next time, that how you use neural network here. Obviously, I've given you clue already that S and T will become neural network. That we already know. So we'll talk about that next time. And we'll also talk about that how will the determinant look like when you have multiple layers. Because then the transformation is through each layer. So how will the determinant look like in that case? What will be the loss function be looking like? How will you use it if your data is a matrix, like an image instead of a vector? How will you do that in that case? Do it in that case. So all of this we'll talk next time. Okay. And before that, in the practical, I will just give a brief overview of neural network. I hope many of you know about, at least some of you know about neural network. If you don't miss Wednesday lecture practical. Anyways, if you want a quick recap of neural network, the deep learning course is already there, so that you can refer. Not the last time one, I could not record, last to last. Okay, I think 22, something like that. Okay, so I'll stop here. Any questions you have, you can ask. Otherwise, we are done for today. We'll meet on Thursday, we'll wrap it up, and then maybe we'll start discussing diffusion a little bit, which we'll finish on Monday. Okay. As I said, practical has been uploaded, last practical. Homework deadlines are near, finish it. And yeah, we have to finalize one date for the final presentation, project presentation of this course. So any idea on that? Any day that you prefer for the project presentation? Or maybe let me put it this way, do you want it before the minor or after the minor? And this I'm specifically asking to UG and those who are having MTP, because BTP and MTP will be on 26th and 27th. So you might be overloaded there at that stage, or it can be after that also. So 28, 29 is also an option, for example. Okay. So think about it. You don't need to answer now, but let me know. Next class I will again ask the same question. That when will you prefer? What is the preferred time for you to have the final project presentation of this course? Okay. Thank you.